FM2 for correlation and regression. The syllabus needs us to explore the relationship between several variables, including calculating Spearman's rank correlation coefficient, Pearson's product moment correlation coefficient, and working out least squares regression lines. Suppose we have to investigate the correlation between two variables, where by experimentation we'll get the following data plot, which is a scatter graph. We calculate summary measures for these two sets of data, bivariate two sets of variables, using the following. So SXX means the sum of each x from its mean and square them, then sum them. But simpler, we can sum each x squared, so sum all the x that's been squared, take away the sum of x all squared divided by n. Similarly, S of yy is worked out as the sum of each y that's been squared minus the sum of y all squared divided by n, and Sxy is worked out as the sum of each product of xy minus the sum of x multiplied by the sum of y divided by n. These are given to you in the information book and are used to work out any correlation. For the Pearson's product moment correlation coefficient R, we use that R is equal to S of xy divided by the square root of Sxx multiplied by Syy. And this gives us a measure of the amount of correlation between two variables. A +1 would give a perfect positive linear correlation. A -1 would give a perfect negative linear correlation, and a 0 means there's no correlation. And any number in between those, say 0.5, would give some positive linear correlation. So anything in between gives us an idea of the amount of correlation we have. Sometimes it's not possible or not worthwhile to measure certain variables, so we use Spearman's rank correlation coefficient instead of the product moment correlation coefficient. For example, suppose a manufacturer of tea produces a number of different brands of tea. You could taste each blend and place them in order of preference. So that would give you a ranking. Therefore, Spearman's rank correlation coefficient is a special case of the product moment correlation coefficient, where the data is ranked first before calculating the coefficient in the same way as above. Or, a simpler way is to use the following formula, where D is the difference between the rankings within each pair, xy. So D squared doesn't matter if the difference is positive or negative, and we can use that to work out the Spearman's rank correlation coefficient. This time, a +1 means that the rankings are in perfect agreement. A -1 means that the rankings are in exact reverse order, and a 0 means there's no correlation between the rankings, and any number in between gives you an idea of the agreement between the rankings. Then, suppose our two variables are related by the equation y is alpha plus beta x. So compare that with y equals mx plus c for a straight line. So our beta is our gradient and our alpha is our y-intercept, or our starting value. Suppose that is the true relationship, then our data plot could look like this, with correct x values and observed y values. And suppose we can then draw a line of best fit through the data to estimate the true relationship. So our line of best fit would go in the direction of the crosses and be so that the points lie fairly evenly on both sides. So we're going to use this data plot to estimate the true relationship. Now suppose our line of best fit now has an equation of y equals a plus bx. Well, our a is our estimate for alpha and b is our estimate for beta. And then each point has a deviation from this line of best fit of di for each point, x, I, y, I. Then to make this a least squares estimate, what we do is minimize each d squared, so it doesn't matter which side of the line we are, and we add those and we need to minimize that. So we get our estimate for beta, b as our estimate for beta as sxy over sxx. And we make the line go through the mean of the two data sets so that y bar would be a plus bx bar. Then our a is an estimate for alpha, so it would be y bar take away the b x bar. This regression line can be used to estimate the value of a dependent variable for any value of independent variable. Our y is the dependent because our x is the independent. So we pick an x value and we can estimate the y value using our estimate a and b for alpha and beta. Interpolation is when you estimate the value of a dependent within the range of data that you've been given. Extrapolation is when you estimate a value outside of the range of data. These can be unreliable and you should not in general extrapolate and must view any extrapolation values with caution because you're not given data around the value that you want to find. In the information book, you are given this under a heading of correlation and regression. So your Pearson's product moment correlation coefficient is given there, R equals. At the bottom is your Spearman's rank correlation coefficient given to you in the information book, and in the middle is your linear regression estimates. So your estimate for B peak, our B is given by SXY over SXX, and your estimate for alpha peak, our A. So our estimate, our least squares regression line is given there. An example. A group of engineering students were assessed by written examination, practical and coursework. The table below shows a correlation between the different method of assessment. So an exam gives you the 1. The exam with a practical gives you 0.655. The exam with coursework gives 0.810. But the practical with coursework gives a 0.971. Comment on the correlation between the exam percentage and the practical mark, between the practical mark and the coursework mark, and then it is suggested that next year only the examination percentage and the practical mark should be recorded. Comment on this. So, exam percentage and practical mark was a correlation of 0.655. There is a positive correlation between the exam percentage and practical, showing a good practical gives a fairly good exam percentage. Between the practical and the coursework, 0.972 is our correlation between practical and coursework. Therefore, it's a very strong positive correlation and shows a close association between the two. Therefore, being as there's such a close association between the two, both are not needed. So little information about the students will be lost if the coursework marks are no longer recorded. Another example. Records of claims following hurricanes in the USA are kept by an insurance company. The number of injuries, X thousand, and the total approximate cost at today's prices, Y million dollars, for each of 10 hurricanes that occurred between 1930 and 2010 are given in the table. The 10 selected hurricanes may be regarded as a random sample. Calculate the value of Spearman's rank correlation coefficient and then carry out a hypothesis test, plot the data and comment. So let's have a look. The first part was calculate the value of Spearman's rank correlation coefficient. So we need to rank the x's and rank the y. So ranking the injuries, so the least we've given a 1 to, and then the highest we've given a 10 to. Then the y, which was the cost, so the least cost was $180 million, and the highest was $3,200 million. So ranking them there. Then we need to work out the difference in the ranking. So 10, 8, 6, that's a 1. They're the same. And then we get a 1 there. So our formula for the rank, Spearman's rank correlation coefficient, would be 1 minus 6 times the d squared over n times n squared minus 1. So our d is a 1 and a 1, squaring those and adding them we get a 2, and that formula gives us a Spearman's ranking correlation coefficient of 0.9979 and so on. Therefore, part B is said carry out a hypothesis test at the 1% significant level to determine whether your calculated path indicates a positive association between x and y. Interpret your conclusion in context of the equation of the question. So our RS was 0.99798. We want that there's no association tested against there is a good positive association. We want a 1% significant level, so one-tailed at 1%. And if you look at table 10, which gives you critical values of Spearman's rank correlation coefficient, we have a one-tailed 1%, which is there, and we have 10 in our sample. So looking across at 10, down at 1, we get 0.733 as our critical value. Now 0.998 is greater than the 0.733, so there is a significant evidence exists to reject H0 and conclude that there is a positive association. This suggests that hurricanes in which there are higher numbers of injuries also result in a greater cost in property damage. Now we need to plot the data on the graph paper and then give a reason why the product moment correlation is not appropriate measure for this given data. Okay, because we use Spearman's, didn't we? So if we plot the data as it's given, and we get a data plot looking like this, with our plots collected at the bottom and spreading out. Now, if we just use the product moment, we can see that it's not going to be a straight line. Therefore, using the ranking, we got a better idea of what's happening, because there is evidence of a non-linear relationship here, or a curved relationship. So using the ranking gave us a better idea of what was happening. Another example. A doctor is interested in the relationship between a person's body mass index and their level of fitness. She believes that a lower BMI leads to a greater level of fitness. So she randomly selects 10 female 18-year-olds and calculates each individual's BMI. The results, the females then run a race and the doctor records their finishing positions. The results are shown in the table. Calculate the Spearman's rank correlation coefficient, and stating your hypothesis clearly, do a one-tailed 5% level of significance for the Spearman's rank correlation coefficient, and then give a reason to support the use of the rank correlation as opposed to product moment correlation coefficient. So first of all, we need to work out Spearman's rank correlation coefficient. Now the finishing position is already ranked, so we need to work out BMI ranking. So if we pick the smallest BMI, there's the formula we're going to need. So ranking them in smallest to highest BMI, and then the difference we want, so the difference between the rankings, the sum of those, square those and add them, and we get 32. So our Spearman's rank correlation coefficient would be 1 minus 6 times the 32 over 10 times 10 squared minus 1, which is 99, gives us 0.806. Now we need to do a hypothesis test. So we've got our Spearman's correlation coefficient there. Now we want to see if there is a correlation as opposed to there being none. We're talking about population, therefore no correlation between the populations as opposed to there being a positive correlation. So using table 10, again, Spearman's rank correlation coefficient, we've got 10 people with 5% now, one-tailed, and we get 0.5636. This is less than our value of 0.806, so our RS is within the critical region and we can reject H0, giving that there is a positive correlation and that a lower BMI does affect fitness levels. Why did we pick Spearman's rank correlation coefficient as opposed to the other one? Well, one of the sets of data was already ranked, so it makes sense to use the ranking for both. Last example. Okay, so we need now then blood pressure against the age of a pupil. 7 hospital patients, the blood pressure is P and the age is T. You are given these values. We need to work out S of PP, S of TP, S of TT for these data. Calculate the product moment correlation coefficient and interpret that, and then draw a scatter diagram, find an equation of regression, plot that, and then estimate the blood pressure of a 40-year-old. Okay, so we need to transfer our SPP into our formula for SXX, say. So SPP should be sum of P squared, which is that one, minus the sum of P all squared over N. So putting the values in, we get 7,270 for SPP. STT would be the same, so sum of the T squares minus the sum of the T all squared over N. And the TP would be sum of each T times P, and we've given them, so we don't have to work them out, minus the sum of the T's multiplied by the sum of the P's all over N, and that works out to 2,369. So we've done those. Product moment correlation coefficient is given as that. So working those out with our numbers, we get 0.701 and so on. Interpreting this, so it's positive correlation, therefore older people have higher blood pressure on average. Draw the scatter diagram. So there's the blood pressure against age, and should give us a scatter diagram like that. So it's fairly positive, apart from a few outliers. Work out the equation of the line, regression line. So regression line, if you remember, was SXY over SXX. So transferring our letters, we get S of TP over S of TT, giving us 1.509 and so on for the gradient B, our estimate. And A needs to go through the mean, therefore we get a mean was sum of the P's over 7 minus the B minus the mean of T, which is a sum of T over 7, giving us an estimate for alpha as 45.467. So there's our equation of the regression line, our estimate for the true relationship. Plotting those, so we need somewhere in the middle and somewhere on each end. So our data goes from 26ish up to 74. So plotting values in there, we get a regression line looking something like this using our equation. And it was asking to estimate the blood pressure of a 40-year-old patient. So 40 is within our data range. So using our equation, we get 105.8 as the blood pressure of a 40-year-old patient. This is called interpolating, as 40 is within the data range. The last question now. A teacher took a random sample of 8 children from a class. For each child, the teacher recorded the length of their left foot and their height. The results are given in the table below. They're from one class. You may use the sum of F is that, the sum of H is that, the calculated value of S of FF is that, S of HH is that, and the sum of FH is that. Calculate S of FH. Work out the regression line, estimate the height of a child, comment on the reliability, and then bring in the teacher. Our SFH means the sum of F times H minus the sum of F multiplied by the sum of H over N. So we've got the sum of F times H, we have the sum of f, we have the sum of h, divide by 8 of the children, and we get a value of 64.75. The regression line. So our estimate of the gradient, the b, would be SFH over SFF. So multiply them over SFF, the x value, and we get 64.75 divided by the 39.5, and we get 1.639 as an estimate for the gradient. It has to go through the mean, therefore our A is given by, an estimate for alpha is given by 97.5. So our equation, our regression line equation is 97.5 plus 1.64 times f. Use your equation to estimate the height of a child with a left foot length of 25. 25 is within the data range. Therefore, interpolating with f25, we get, using the equation, we get 138.5 as an estimate of the height. Is this reliable? It should be, as 25 is within the range of the data. The left foot length of the teacher is 25. That's within the data range. But this data set worked out that regression line, but it is for children. Therefore, a different equation should apply to adults. Or you could say that the children are still growing, therefore the height will increase more than the foot length as they get older. So a little bit of thinking to do there. And that is the end of the video for correlation and regression.